With that, it brings us to the end of this Q&A session. We need to move on to the next talk. So thank you very much, Suresh, for your time. Much appreciated.
Okay, thank you. Okay, signing off. Bye.
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 So we're going to move on now to our next second talk of this webinar, and that's by Professor Moataz Attallah from University of Birmingham, and it is titled Additive Manufacturing of Nickel-Based Superalloys, the Outstanding Issues.
So I'm going through the review paper on additive manufacturing of nickel-based superalloys, highlighting the outstanding issues remaining in that field. My name is Moataz Attallah. I work at the University of Birmingham in the School of Metallurgy and Materials. The paper was co-authored by my colleagues Luke Carter and my PhD student Rachel Jennings and Shishan Wang. Nickel superalloys are one of the key materials in the field of aero-engine materials, but also they are heavily used in the power generation sector. They have various other applications in the space field because of their high temperature capability. As you can see, this is just a schematic diagram of an aero engine from Rolls-Royce showing where nickel superalloys are used, and as you can see, they're typically employed towards the hotter end of the aero engine. Most of the components there are either forged materials or cast materials. There's also the single crystal nickel superalloys, which are used to take very high temperatures towards the back of the engine. In fact, nickel is probably the largest amount of material by mass within an aero engine actually is for materials made out of nickel superalloys. But nickel superalloys are rather complex. They are basically contain more than 10 alloying elements in some cases. They can be even more complex beyond that. They contain elements like chromium, for instance, that is used to improve their oxidation resistance, as well as elements like titanium and aluminium that form precipitates to strengthen them. In addition to other alloying elements like molybdenum, cobalt, niobium, zirconium, boron, and iron. And these different alloying elements have various roles in the nickel superalloys achieving their properties that we require. As a matter of fact, the way that the microstructure behaves is rather complex, as a matter of fact, since some of these elements partition to specific phases. So for instance, we find that the boron, for instance, can partition to the grain boundary. Titanium and aluminium, they partition to the gamma prime phase, which is the strengthening phase in nickel superalloys. Some other materials like the niobium, it partitions also to the gamma prime and gamma double prime. So the role of the different elements can be quite difficult, and that adds to the complexity of nickel superalloys in general, and also the complexity of how we think about them as a material to be used for additive manufacturing. I mean, the following slide is probably just to further strengthen the previous point I mentioned. It shows what role the alloying elements play in terms of the performance of nickel superalloys. So some elements are used for oxidation resistance, some ones are used to control the precipitates and their types, some other ones like tantalum and tungsten rhenium can be used for solid solution strengthening. But overall, if we're dealing with a material that, as you can see, at least attracts, or an alloy class that attracts at least a dozen alloying elements, you would expect that this will become rather complex when it becomes, when you look into its processing by any manufacturing technique. So over the last 6 decades or 7 decades or so, nickel superalloys have gone through a significant development. All the time we were seeking a higher temperature capability in nickel superalloys. Initially in the 40s and the 50s and some of the 60s, we were looking into the development of the high temperature capability, and initially we started with wrought or forged materials. And eventually we started to look into more complex applications, into blades that can take higher temperatures, and then casting of other materials like Inconel 713 and 738 and 247 started to appear between the 60s and the 80s. But then from the 90s and beyond, we started to move into directionally solidified superalloys and then eventually into single crystals. And as you can see, looking into how the temperature capability of nickel superalloys evolved within the last 60 years, you can see that we evolved approximately 400 degrees in its the temperature for their creep life at 137 megapascal, as shown in that diagram. Now, how is that all relevant to the concept of additive manufacturing? Moving in the alloy chemistry and moving in their high temperature capability also meant that we have to move in their chemistry. We have to design an alloy that's capable of giving us a high temperature performance. And as a matter of fact, that resulted in us in adding more alloying additions of elements like aluminium and titanium, which can strengthen the material by the formation of the gamma prime phase. We also added some other elements like cobalt and chromium to increase the higher temperature oxidation capability and also the control of the phases that are present, like the carbides, within nickel superalloys. And as a matter of fact, the more we added of these alloying elements, the more it became difficult for us to weld these nickel superalloys. Basically, additive manufacturing is like welding. You're welding many layers, and instead of welding, few layers as in a weld bead or so, you're welding maybe hundreds or thousands of layers every time you're building a component. And as a matter of fact, the same issues that we see in welding of nickel superalloys will be the same issues we see in additive manufacturing of nickel superalloys. So this diagram that we see in front of us shows a qualitative indication of the weldability of nickel superalloys as a function of the alloying elements. In that case, on the x-axis, you can see the chromium and cobalt as one factor. There's an equation here, 0.28 chromium plus 0.43 cobalt on the x-axis, and then the aluminium and titanium on the y-axis, which are actually the elements that form the gamma prime phases. And what you will find is that the higher the amount of the aluminium and titanium content, we end up getting more difficulties in welding. So that qualitative classification we see on the diagram shows the typical alloys that people have used in the 40s and the 50s as alloys that are readily weldable. But as we move in that high temperature capability of nickel superalloys toward materials like CM247, we start to appear in the difficult to weld envelope. So what is the real difficulty in welding or additive manufacturing of nickel superalloys? What's the difficulty in making multiple welds of that material, which is the same thing we see in additive manufacturing? Basically, nickel superalloys, when we weld them, they are typically exposed to, or they can be prone to 4 mechanisms of cracking. The first one is solidification cracking, and that's similar to cracking that we see in many other materials, not just nickel superalloys, where typically the freezing that happens combined with the segregation that's happening during solidification results in the formation of weak regions, which then, with the presence of tensile stresses during consolidation, during shrinkage, they can inhibit the backfilling of the interdendritic regions, and as such will open up cracks, dendritic basically cracks, and will act as crack initiation points during solidification. So that's one thing can happen in nickel superalloys with the complex chemistries we see inside them, that when we are basically building a component by additive manufacturing or even by welding, we are likely to get that mechanism of cracking. The second mechanism is called liquation cracking, and this can usually combine with rapid heating and of the material, typically away from the melt pool. So we're talking here about the material which is below the molten region, not just the molten region, but actually what's a little bit far away from, or a little bit close to the molten region, but not in the molten region itself. And some phases will end up actually forming a melt pool, or forming a liquid film that then will form basically a crack that then can act as a crack initiation point on the tensile stresses. The third mechanism, which is reported a lot in nickel superalloys literature, is the mechanism known as ductility dip cracking, which is believed to occur as a ductility reduction for the material in intermediate temperatures. And this reduction in ductility seemed to exist in the grains that show, as you can see on the top micrograph, top right-hand side micrograph, fairly straight boundaries. The mechanism itself is not fairly clear about why it happens, but we are talking that there's a chance that it's accompanied with the presence of phases like carbides causing incoherency on the grain boundaries, combine with the residual stresses, resulting in the formation of cracks. Then the fourth mechanism that we also are aware of in nickel superalloys is the mechanism known as the strain edge cracking, where typically if you weld the component, that welding process with its rapid heating and cooling phases will result in the formation of residual stresses. So those residual stresses, when we apply a heat treatment to relieve the residual stresses, the competition between the gamma prime precipitation and the relief of residual stresses will result that at a point the material will have combined stresses from the shrinkage related to the gamma prime formation and the ductility resulting from the presence of cracks. And as a result, cracks will open up. In simple terms, typically you will end up building a material by additive manufacturing or welding it, and when you weld it or build it, it doesn't show any cracks. But then you expose that material to a stress relief heat treatment, and it actually cracks within the post-weld heat treatment process. So, and that's what's known as strain edge cracking, or post-weld heat treated cracking. So any of these four mechanisms, they can, in the same way that they happen in welding, they can happen in additive manufacturing. And for a crack to happen, as it's obvious within the four mechanisms, there has to be another element, which is residual stresses. And that adds to the complexities we have in additive manufacturing, that the process involves repeated heating and cooling, and as a result, we need to control the residual stresses that happen, or at least understand how they evolve. There are some good reports in the literature talking about the residual stress development in additive manufacturing. This is the results from one paper by Professor Das, looking into the distortion due to electron beam selective melting in Inconel 718 nickel superalloy. 718 as an alloy is known to be weldable. Actually, it's an alloy that you can build with additive manufacturing without seeing significant amount of cracking. But what you can see is that the substrate where the component was being built in figure D and C, you can see the amount of distortion that the component has seen. And that's significant. Obviously, that's a significant deviation of tolerances, a significant deviation of the required performance of the parts, and in most cases that will require a post-processing treatment to be able to control the residual stresses. But one of the key things that people have been active in developing to understand residual stresses is process modeling. And as you can see that with the process modeling, you can get an idea about the amount of distortion and the amount of stresses built within the material. And as a result, you can change your process sequence, or you can change your process parameters, including the scanning strategy, how the heat input is being applied, in order to reduce the stresses available in the material as you build in the as-built condition. There are some reports also that looked into this in a different way. This is a study that came out from Fraunhofer ILC in Germany, where they looked into the influence of the scanning strategy. So basically, this is more like a comb-type structure with like a tooth, as you can see the teeth at the bottom, and they tried two different scanning strategies. This first one is A, where we're using short scanning vectors, and in case B, we're using long scanning vectors across the entire length of the component. And as you can see that the short scanning vectors gave a slightly lower distortion, which in our case, basically that explains that it has lower stresses inside, lower tensile stresses in that component. The component was validated, so they built the actual component, and then they used wire EDM to cut the teeth of the comb, basically, except for the left-hand side end. And the amount of relief that you get because of the release of the stresses can be used qualitatively to indicate the amount of distortion. But the key point we want to see here is that the process itself can be rather complex, and one change in one of the parameters, which is in this case the scanning strategy, will control the thermal fields, and as a result will also affect the amount of distortion we're getting out of the process. The second thing that we discussed in the paper was the process optimization. How do we go on optimizing the process parameters in additive manufacturing? for quite some time, people have been using the energy density model, which is basically an equation that lumps together many of the process parameters in a single figure of merit, single factor, that indicates how much heat we're giving to the material, how much energy density, as a matter of fact, is being given to the material. And that equation, that simple equation, the power over the scan speed, V, times the hatch or the overlap spacing, in some other versions, we have the power divided by scan speed times hatch spacing times layer thickness. So generally speaking, this equation was used to correlate the heat input with the scanning, with the amount of, with the defects that form in the process. In one of our reports that we published, we showed that the increase in the energy density is typically accompanied by the reduction in the porosity. So the red squares or the red diamonds show a reduction in the voids or the porosity until a certain level. We call it the threshold energy, which beyond that, typically the porosity stays within less than 1%. But the second factor we see is the cracking, and we do not see significant correlation here between the cracking density, which is the blue squares, and the energy density. As a matter of fact, it seems quite random to some extent in this equation. So that approach can give us an idea about a starting point, how much energy we need to give to the material to enable its consolidation, but it doesn't correlate much with cracking density. And in many cases, the challenge we have is we have two problems to solve. As you can see on the left-hand side picture, there are the cracks, the ones that are arrowed, and then the porosities, which is encircled. And basically we're trying to see if we can reduce both at the same time. In many cases, reducing the porosity means giving high energy, but reducing the cracking meaning giving lower energy, because the higher the energy, we're creating more residual stresses in the material. So there's another report we also included in the paper, whereby we combine the data from 4 different studies that looked into different nickel superalloys. So Inconel 718, 625, 486, 247 in different conditions. And we found again that to process nickel superalloys, you need to achieve that threshold energy density, a minimum level of about maybe between 1.3 to 1.7. Beyond that level, you end up having very low porosity in the material, less than 1%. But that correlation did not hold, as I mentioned previously, when it came to cracking. We still had basically an increasing trend of cracking density with the increase in the energy density, but there was still some scatter in the data, suggesting that maybe that model is good enough to look into the porosity, but it's not the best when it comes to looking into the cracking density. Now, where is the future heading in additive manufacturing of nickel superalloys? One thing that many studies have shown, and as a matter of fact, it's available on the cover of the MRS Bulletin issue, it shows that one of the flexibilities we can have in additive manufacturing is that we can control the microstructure. So if you look, for instance, the typical microstructure we get from additive manufacturing, we end up having columnar grains in some cases, extending from the bottom to the top of the build. But we can still, by changing one parameter, like in the case of B and C, we change the scanning strategy from unidirectional to bidirectional scanning. We can see that we can grow the grain size a little bit. And as a matter of fact, if we increase the energy, the laser power, we can end up getting epitaxially grown grains from the bottom to the top with fairly columnar grains. And combining these things together means that we should change the way we look into additive manufacturing from just making a shape or making a component with specific properties and microstructure into making a component with more than one microstructure, with the microstructure being tailored to the performance of the final component required. Then the last challenge, of course, we have to address with additive manufacturing of nickel superalloys is the mechanical properties. Obviously, if you want to make a component, we want that component to achieve the correct mechanical properties. And there are some studies now in the literature that shows that there is an increasing importance for the use of a post-processing method like hipping, like using hot isostatic pressing. So the study by Blackwell showed that you can achieve UTS and yield strength of, in fact, exceeding what we get from the forgings just by doing a post-processing and heat treatment procedure involving hipping and heat treatment for Inconel 718. And that is obviously shows that it's in some way a necessity actually to use post-processing in many applications, just the thermal post-processing in this case. And if you look into even the ASTM standards on Inconel 718 and Inconel 625, they both actually indicate that hipping is used whenever there is a need to maximize the performance. There aren't many data in the literature yet on the fatigue behavior of nickel superalloys additive manufactured components, but tensile results have been promising, and I expect the results that involve creep and fatigue to appear very soon, and then we'll understand if we can improve the performance by post-processing of additive manufactured component. So in conclusion, I highlighted in this brief talk, give an overview of the topics we discussed in the paper, issues like the residual stress development, the microstructure properties development, and process optimization. We still have to do some more work in that, the combination of modeling and experimental verification of our finite element models and other models to look into how we can control the residual stress state, and the microstructure and properties development is equally important. There are some useful tools that we can use, like the energy density method or simple modeling tools, to get an idea about how the parameters affect the performance. But we also expect that in the future, we hope that the additive manufacturing platforms will improve in their flexibility to allow us to design the microstructures and control the process in a more efficient way to reduce the residual stresses or maximize the mechanical properties. And I thank you for your attention and for giving me the chance to talk through our paper with you on this. Thank you.
Hello, everyone. This is Suman back here. I'm going to address some of the questions that were posted during this presentation. I've done quite a bit of work on nickel-based superalloys myself, so I'll do my best to try to address these questions. I'll start with one that was asked previously towards the end of the previous talk, which was, is there a general lower limit on the particle size that is defined? There are some practical limits in terms of the particle size of the powder that can be used, and that has to do more with the ability to spread powders. As powders get finer below about 5 microns in particle size, it becomes increasingly difficult to spread these powders uniformly across a powder bed, and one can end up with situations like clumping and other issues. So certainly being able to spread nanoscale particles presents many challenges. There are some groups that are working on it, and we'll have to see the outcome of those if they're able to innovate some new methods in being able to lay down extremely fine powders. One of the questions that is asked is, how significantly will the geometry of parts affect residual stresses, and how to model them accurately? Will this detract from the benefit of complicated geometries that AM can provide? So yes, the geometry of the part does definitely affect how residual stresses get built up, especially when you're looking at rapidly changing geometries, when you have cantilevers, you have changes in cross-section, the residual, and especially when you're looking at building up parts layer by layer, and you have a new segment of a part that does not have a layer underneath, but rather has powder underneath, then the thermal boundary conditions there are different, and that can then lead to different residual stresses that can build up, especially when you have rapid changes in cross-section. And so that does present challenges, especially when you are looking at having to model the entire thermal history of the part. And furthermore, another important question is, how long does the part remain buried in the powder bed, and at what temperature do you take it out, and how does that part cool? So those things all affect any kind of distortion that may occur. So there's distortion that occurs during the process, and there can be distortion that occurs after the process, depending upon when and how you took the part out of the bed. Another question that was asked was, can the energy density model be applied generally to any additive manufacturing technique? Well, the energy density model that we are familiar with, which is power divided by the scan speed and the hat spacing, is particularly relevant for laser or electron beam-based processing. And it's even more so, it's particular and it's very well suited for a rectangular geometry if you have a constant scan vector length and you are actually just rastering across or sweeping across a rectangular box that's being filled. If you have a widely varying cross-section, then the scan energy density is an approximate metric that can be used. It's not very representative of actually what's going on in the powder bed. Another question here that's being asked is 3D metallic printing is expected to prepare very complex objects which cannot be easily prepared by conventional methods. This may also mean that the characterization of mechanical properties of these complex objects from 3D printing also need new approaches to evaluate their quality rather than just hardness and tensile, etc. Yes, I think that's absolutely true, because it is highly likely that with complex 3D objects with widely varying cross-sections, the microstructure in different regions of the part is going to be different. The grain sizes are going to be different. So if you take an as-built part that has a complex geometry that's coming out with thin and thick cross-sections, there are going to be spatially varying mechanical properties. And this is partly the reason why many practitioners of metal 3D printing today are applying post-process heat treatment and hot isostatic pressing to more homogenize the microstructure, to eliminate porosity, and to drive the microstructure towards microstructures that have been previously well understood from conventional manufacturing approaches. And once that is done, then there's a reliable way or a good way to be able to predict what kind of properties are coming out of the part. So there's going to be a comparison between as-built properties as well as properties that are being attained through post-processing heat treatment schemes. And I think that is something that's going to have to be taken into consideration and accepted as post-processing that's going to have to be required in order to get some kind of microstructure that's well understood, because the microstructures coming out of metal 3D printing are quite different and quite novel. They're quite different from conventional microstructures obtained through conventional approaches. And so being able to compare to something that's been well characterized and understood, and also to kind of homogenize the microstructure properties post-process treatments are going to be required. And those are already being practiced today. How can you ensure, here's another question, which is how can you ensure confidence levels for AM material and qualify the material given the issues with reliability? So most metal 3D printing techniques, especially the powder bed based ones, are known to produce defects such as porosity, lack of fusion between layers, and even some levels of cracking. And so a lot of work is being done to characterize the properties of these fabricated structures that have already inherent, that have defects that are occurring as a result of the process. In many cases, those defects might be potentially removed through post-process hot isostatic pressing. In some cases, the defects cannot be removed, and therefore certain acceptable levels of defects have to be taken into consideration, have to be accepted, and on the basis of that, allowable ranges of properties are being presented to designers to take into consideration when they're designing parts. So design allowables based upon levels of defects that are present in 3D metal printed parts is a major area of activity today.
So, Dr. Das, I know that you had something of a hard stop. It's 32 minutes after the hour. Do you want to wrap it there?
I think so, Bob, because we are at the end of the questions that have been posted. So I think I've addressed most of the questions that were posted during or after this second talk. And I think at this point, I'd like to hand it over to you to conclude this webinar.